Hello everyone, my name is Vahid. I'm the Senior Director for Engineering Services at Maplesoft. Today I'm going to be talking about the dynamics of mechanical systems. The majority of this talk today will be focusing on roll-to-roll systems. So I'm going to be talking about simulations and specifically try to give you some examples and explanation of what do we mean by simulation, um, how to perform simulation specifically on a web line, and why should we use simulation in engineering. So first off, simulation. It can take a variety of different forms, from automotive and vehicles, converting systems, heavy machinery, robotics, satellite, thermal systems, just to name a few. So it can take very different shapes and forms. And what we see here in these examples are only the parts that move. There are additional parts, right? Hydraulic circuits, pneumatics, electrical parts that are not visualized but part of the simulation of a system. So a simulation in our world is usually we call them system level multi-domain simulation. And this is based on analytical models like first principles, such as Newton laws of motion, conservation laws, and such. It could also include semi-empirical models and also empirical models, which we can include in a broader simulation. In addition to that, we use mathematical pieces as well, such as filters or gains or feedbacks. So all of them together uh, are the parts that build up our approach to system level multi-domain simulation. So these principles are then categorized to physical or engineering domains uh, that we group already built component models that we can then put together to build more complex systems, such as what we're looking at here, which includes tires and interaction with the ground, hydraulic system, mechanical systems, and all of that. Here's another example of a crane, which includes block diagram on the left and the 3D visualization of that on the right. Again, we bring different component models from these libraries, connect them together to build more sophisticated systems. But today, here, we're going to be focusing on the roll-to-roll converting. So let's look at the web handling library. The library includes groups of subcomponents for spans, for rollers, or nip rollers, source and sink, or wind and unwind, one web or multiple webs, components to allow you to merge multiple webs together, component to allow to split a web into parallel strips, additional utility component to move things around or connect things together, and drives, electrical motors, and controllers to create feedback loops and create a complete system. So before we go into more of modeling, I thought I should include a little bit of a behind the scenes. And from all these components that could have a lot of equations embedded in them, the simplest one is the span component. So I want to talk about that a little bit more from the equations or the equations that are used in those components. So span is everywhere between other components. You will have a span connecting rollers, wind unwind drums, and nip rollers. So let's look at the equation that goes to that component that we use to build models from. This is very well established, and in its simplest form, we have the conservation of mass equation as the constitutive equation for a linear damped model here. And this equation include the web properties like homogeneous elasticity, cross-section, Poisson ratio, and damping. But since we have these equations, we can technically simulate the model without a block diagram approach. And I included these piece here to just show you what it would take. So we typing the equations. I'm using a Maple environment to do this direct equation solving. I need to provide the numbers for the web properties, boundary condition, the velocity going into a span, coming out, and the strain going into the span. Configuration here is just the length of the span, and then we solve based on the information we have, and we can then plot the variation of, for example, tension over time. We get the familiar curve of gradually reaching to the steady state maximum tension, and if we increase the speed of the web, we'll get there sooner. And for example, if just like the draw systems, if we increase the outgoing speed midway, we'll have a jump in the tension. But you can imagine if this much work is required for just a single span, if we add rollers and tens of spans and rollers and nip rollers and slippage and all other approaches, maintaining it, if not impossible, would be very, very difficult. That's why a block diagram approach makes it much easier to basically have the software write the equations for us. We deal with the blocks on the screen. We drag and drop, very similar to the web line that we want to model. And the equations are generated behind the scenes and then solved numerically. So some comments about this, that doing this approach, we have a large library of pre-built component models like nip rollers or spans. It's very convenient to create models with many, many spans as opposed to going it direct. Since you are in a multi-domain in a modeling environment, you can benefit from other domains available like hydraulics, pneumatics, and electrical. We get as we saw, we get the visualization automatically generated for us. Block diagram is also makes your model readable and easily modifiable. Since at the heart of it, still the same equations, we get access to everything that is used to define those component models: stress, strain, tension, width, variations, and so on. Some benefits are that this approach calculates the length and the wrap angles automatically, so we don't want to go there and have the software do it for us. And being in this environment would provide additional benefits, and we'll talk about that a little bit later, to perform a more automated task like optimization or parameter sweep, or doing scripting to automate some of the pre and post processing requirements. So let's now talk about how or what we need to do a simulation of a web line. Really, the answer is really going to be relying on what question we want the simulation to answer for us. There is no general recipe for creating a model, but here is a kind of a step-by-step look at increasing fidelity of creating a model. So first step is basically creating the skeleton of your model. Obviously, we need to know where each axis is and what is the diameter of rollers. Then additional information like the length and the mass and inertia of those rollers. This is the dynamic simulation. So that could play a part in the type of results that we're after. Moving parts need to be included, like dancers or accumulators. So we need to include those as well. that would potentially play an important part in the simulation results. Then, of course, we need to include information about the web that goes through our web line. Not every information required or listed here for the web would be of same importance for the type of simulation we're doing. For example, if we are under torque control for a stiff web, which with very, very low strain, with no concern for resonances, then the modulus of elasticity, having it accurately, is not as important as for a soft material that goes under large strains and large width reductions. Additional details that we can include in the simulation, again, depends on what type of system we are dealing with. For example, bearing drag might not be an important factor for systems that have high baseline tension, but for systems with low baseline tension, the bearing drag could be of much more of higher importance, and knowing it accurately would play a part. To get from a model to something that resembles more the actual system, whether it's a new design or an existing design, we need to include the counterparts for the sensors on the system, like load cells, encoders, and the roll radius sensors. Then we start to set up the model to perform a process similar to the real machine by including actuators like motors for the pull rollers or nip rollers, and nip actuation, the whole speed profile of running sequence, and feedback controllers. We can increase the fidelity of the model if the need be by nonlinearity, web sag, or even air entrainment. Then once we have this type of models, we can benefit from any available measurement data to try and tune the parameters to get a validated model. Once we have gone through this step, we are going to be at the point that we can use the model at hand for simulation-based engineering. Just to review these levels that I have dispersed just a moment ago, although I call them level, that doesn't mean that these have to be applied in this order. These are really more like tasks that you need to consider, and obviously creating a web line skeleton and basics would be essential, but after that is all going to be depending on what is available and what is asked. So some tasks will be important, like web properties for certain cases, but some other tasks would be optional if we need to get to an answer quickly, or we want to just compare and get an answer to which design or which variation is better. So here I have a demo web line with some familiar pieces. We have on the unwind and unwind motor. We have a rotary dancer with a feedback from the dancer angle to speed control the unwind. The dancer provides the tension in the unwind zone. You have a SRAP as an infeed with a set velocity on it. And on the rewind, you have a load cell with a feedback for the rewinder. So we can go ahead and simulate this, but just some comments regarding some of the important properties. Obviously, we have the material properties: width, thickness, density, modulus of elasticity, Poisson ratio, and damping factor. Building such models, we usually highlight the parameters that we are more interested in manipulating or changing, so we can create parameter blocks for ease of use. So this is the process. Setup very simple: maximum velocity of the line, the tension in the unwind zone, and tension in the rewind zone. the unwind being set by the dancer and the rewind by the controller. And we're going to focus a little bit later on the SRAP and its configuration. So parameters for friction, web roller friction, and also the angle for the SRAP configuration is also highlighted here so that you can easily change it and start doing some comparisons. First thing first, let's look at the simulation results as we have it here. As I mentioned, once we run a simulation, we get access to everything. Here I have the plot of tension in all of the spans and the 3D visualization of the web line. Here we see the effect of the acceleration during the first few seconds of this particular demo simulation, how it affects the two tension zones by increasing or decreasing the tension in various spans. So right here, without really doing anything else, we could basically investigate the effect of ramp up speed profile or the density of the rollers on these tensions. Minimal information really would be required to get here. There's, in my experience, dealing with a lot of different systems from different industries, it's seldom that everything that simulation could possibly want is available with confidence. So we need to make engineering educated guesses for the parameter values, and sometimes we don't really need them for the questions that we try to answer. This basic model can already tell us a lot about how the system works, and we can do variations and compare. Comparison, it really comes before validation and also after validation of a model. Once we have sufficient confidence of the behavior is correct, we already can vary design or system parameters to see whether that's the right direction to go or not. And it doesn't need to be the final model before we can start extracting engineering information. We can always do that step by step, as we saw in my previous slide. So let's look at one case to use simulation to answer a question. This is a fairly straightforward question, as in what angle should we set the SRAP to minimize the chances of slippage for our infeed. So we have set up for the system the unwind zone at 30 newtons and the rewind at 50. Obviously, the tension difference and the wrap angles and the coefficient of friction are some of the prominent factors in if we're going to have slippage on the SRAP or not. But let's try to use simulation to get us there. So what we're doing here is once we have the model, we can use a scripting, for example. There are multiple ways to run a lot of simulation very, very quickly and basically vary one or more parameters of the system and see what we get. Here, what we're doing is we're running the system 100 simulation and changing the angle of the SRAP from minus 30 degree to 30 degree. And we look at two specific output from the system, which we'll talk about in a second. So here we have the wrap angle, pretty obvious as we rotate the SRAP counterclockwise. The wrap angles increase, or when we turn it clockwise, the wrap angle decrease. And we know by decreasing the wrap angle, we'll have definitely less traction capacity. Here is one of the internal calculations are used. We call it summary limit. Basically, it's the ratio of the current tension difference on two sides of the roller divided by the maximum tension difference dictated by the capstan equation. So we don't want to reach 1. We want to be well away from 1. And we here see that just before 20 degrees, we are definitely going to be in the slipping zone where we lose our speed control for this web line. So we want to be as far away as that number as technically or physically possible. So just again, general comments. Once again, we don't need to have the perfect system to come to such type of conclusion. Variations and comparison is really powerful tools that simulation provide. You can even compare different systems with different pieces, like having a nip roller instead of the SRAP. And once again, emphasizing that the model can be gradually improved. But the approach to modeling will give you a lot of freedom to pursue what-if scenarios and check them out and see if you can find another potentially innovative path to improving the system. Here's another more dynamic example. Let's say you have a system that could have periodic excitation that could come from eccentricity or maybe an embossing process. Those or something else that could inject some periodic excitation in the system. And we want to know whether we have a risk of resonance during the variation in speed in the web line. So here we can use an app and benefit from the equation-based approach and see what type of natural frequency the system has, as you can see in this plot for the reference model we just looked at. But let me look at the first two of them with the animation of the mode shape. So the first one for our current setup is around 7.3 hertz, and we see that the most motion is on the unwind zone. And if we go to the second mode, we see a different behavior in the mode shape or the distribution of energy for that mode or potential paths to exciting that system. So this is potentially an important information during the operation of the system of how the real scenarios could create unwanted behavior from the web line. And this is a consequence of the approach we're using here, where we are very tightly connected to the equations, and that allows us to do this type of analysis in a real system as we have been seen in working with our customers. This is really just one part of the solution. We do a lot of signal analysis on the measurement data and simulation data to identify the frequencies that exist. And we do that in the same environment that you saw me just solve the differential equation, and that is Maple. This is some of the consequences of as we can check to see if there is conflict. And having this knowledge of the mode shape for any natural frequency is also important to know whether that is a possibility of that mode getting excited or not. So that the last example that I wanted to conclude with here is running a system with different material. So the one in the back is our original model that we saw, running the original web properties. And without really changing anything, we have just trying to run a much softer material through the same web line. But clearly see that the system as set up for the stiffer material is not behaving as expected, and potentially the variations of tension could lead to breakage. The point here that again wanted to make is that once the model is sufficiently close to intended system, meaning here the original model, then we can learn a lot by studies, by changing the parameters and see how the system is behaving. And that will tell us whether we are going to face a problem. And if we are facing a problem, it will give us a lot of options to experiment with different things to solve it by changing the tension level, changing the feedback gains, and find a good way to fix the system. So thank you. That brings my presentation to an end. And here we can have Q&A.
Thank you, Rang. That was really helpful to see some of the technical tips that you have as engineers are starting to look through challenging issues and how they kind of come across that. Again, if you have any ch questions for Orang about the setup or even bringing your own situation to light, please type them into the chat. Orang, the complex models that you showed, they have a lot of system variables as inputs. But maybe one of your examples, you mentioned that the bearing drag, for example, was had a relatively small impact on the overall performance. How do you kind of come to the conclusions of what you need, what level of details you need to study, and what is is kind of irrelevant or not worth the effort for simulation?
Yeah, thanks, Alex. That's a good question. Um, I think the key really is that the modeling and simulation project is done step by step and gradually. We don't jump to the most complex version of the model first. We start by creating the basic model, learn about the behavior of the model with the knowledge exists from the actual system or the experience that exists. We can decide what type of additional detail we want to add to a given simulation model. The bearing drag, for example, is one of those parameters that is not available in all cases, at least in the many examples that I have provided support, collaborated with our customers. That number is not always known. I would say majority of cases that number is not available, but most engineers have a good idea of what type of ranges we are looking at. Depending on what the simulation is telling us, we can decide whether we want to look further into it. A lot of models, for example, start by assuming our bearings are ideal to get a feel for the what type of tensions we are dealing with, and but then there are factors that might push us to start looking at things like bearing drag earlier. As I mentioned in the talk, that for low tension cases, we had a case with a manufacturer that they were looking at a piece of their web line and they were seeing different behavior when the web goes forward versus backward. And in their case, the tension was very low, and the way the drive and feedback was set up, the difference in the bearing drags would able to very nicely explain what they were seeing in the real system. So it is good to have that option available. And again, the whole point of this type of simulation-based engineering is we add what we need for the question that is being asked.
Right, right. And the one of the later examples you had with the two side-by-side machines where one thing had changed, the material in that case, the simulation allows you to change multiple things at once, though, not just like a single material. You could also potentially move layers, the layout of the rollers or change a wrap angle configuration setting that could be moved into a recommended spec sheet for a customer's needs.
Absolutely. I mean, that example follow up very nicely from one of the points Steve raised as well, that the machine is purchased or commissioned for a particular material, and then something else is run through it. And having a good enough representation in simulation allows you to kind of look into what type of problems you could potentially deal with if you run a different material through it. And in that example, the softer material clearly wasn't suitable for the setup that the model was created with. But to answer your question, absolutely. I mean, in a troubleshooting process, it's always good to don't change too many things at the same time. I mean, you can, but if you want to start comparing, taking notes, figuring out what change did what outcome, you start small, you get to know, and then you continue. For example, in that model, I didn't get to solve the problem, but you could have changed some of the gains, and this would have improved the behavior of that particular model. As you mentioned as well, we have some other. I think they are mentioned in some of our currently YouTube videos as well. Like you have a slippage and you solve it by just moving some rollers around, creating a larger wrap angle, and you get what you expect. That issue goes away, or you play with other types of variations like adding vacuum to improve your traction. So these are the kind of things that simulation make it easy, even if you might not necessarily want to choose it in the simulation and virtual world. Everything is next to free, so you can just try it to see what type of potential paths are in front of you.
I did get one question just asked directly to me, which was the there was some controls and driven rollers, I think, in some of the, like you had the dancers and actuators and so on in the models. The question was, is there a way to model non-linear inputs for driven rollers or the braking systems?
Yeah, I mean, I mentioned, I mean, purposefully, I started my talk by talking about what the simulation environment is that we are performing all of these roll-to-roll converting simulation in. And that simulation environment is a general purpose simulation environment for dynamical systems. So if we want to add nonlinearities, different types of function, even custom function, there is a lot of flexibility. So the answer is absolutely yes.
Very cool. Well, thank you very much for your time, Irang. This was really cool to see the models in action and see an engineer's eyes of what simulation can bring to the table. So appreciate your content and thank you for presenting today.
Absolutely. Great to be here. Take care.
Thanks.